Hello, and thank you for joining Sigrity's webcast today. For the next 1/2 hour, we'll be focused on design-side considerations for EMI analysis and optimization. We'll actually have 2 Sigrity presenters today. We'll start off with Brad Brim. Brad is a Sigrity marketing manager, and he'll focus on EMI issues that can be a challenge for board design teams. And specifically, he'll talk about how analysis can really help improve designs. Most of the time will be spent with the second speaker, who's Tanit Burchapunkt. He is Sigrity's product marketing manager for our Optimized PI product, which is an award-winning product that we introduced in 2007. And what he'll be focused on today are some brand new capabilities that go inside Optimized PI that are focused on EMI optimization and automation around that. So once again, we'll be taking questions via the chat window. We have a lot of people online, so we aren't able to have the audio for all of you live, but I will be watching the chat window. So we're going to start out with Brad, and I will turn it over to Brad now.
Hi, everybody. This is Brad Brim. I'm going to talk for a few minutes about the underlying analysis capability of some of our Sigrity products. I have a background in antennas and EMC type issues, and so if there's any detailed questions afterwards, we can certainly address those through the chat line. Sigrity has a couple of products in time domain and frequency domain analysis for boards and packages that address emissions. What we do is we target board and package designers, not so much EMC compliance engineers. And we'll get to that difference in just a minute, but the design objective and the analysis that we produce is really for board-level EMC issues for board designers. And it's design-side consideration of emissions. And that means what we're focusing on is the board design process itself and the issues that board designers can influence with their layouts and signaling. The objective is more quiet first-pass designs and therefore faster time to market with this predictive design process, because your first designs will have lower emissions and you should have less physical prototyping involved in the EMC loop towards the end of the product cycle. It's very quick and very easy to get started with design-side emissions. And the reason why that's true is because there's signal integrity and power integrity analysis that are being performed for these boards already. And EMC analysis is really just a post-processing step on top of those SI and PI type analyses. In other words, if you set up a DDR bus and you understand how the signals are switching, and you're happy with the signal and power integrity, then it's a trivial matter to take those currents and voltages that are calculated as your SI-PI analysis and propagate those to the near fields. Next slide. There are different roles and responsibilities between board designers and package designers. And on the left side is the target audience, where we're creating designs that meet specifications for proper signaling, for low power, and maybe to some extent in the past for low emissions. Typically, an EMC engineer, whose roles and responsibilities are on the right, would be a consultant acting, and his role would be to provide design guidelines that help the board layout engineers do the proper capacitor placement and maybe power delivery plane shapes. The tools that are used by board designers are schematic and layout and DRC, and to some extent circuit simulation and even EM simulation tools. And that's where the Sigrity contributions for predicting emissions come in, is we take the layout and we do post-layout analysis in a hybrid circuit and EM simulation environment that can predict emissions. Next slide. If you look at a classical product design chain up at the top, you design the PCB, you lay it out, and you do a physical prototype, and then you do emissions testing. Well, that's really the first time that you've done any analytical EMC consideration. Even if you've done some design rules and had some consulting from an EMC compliance engineer on the layout, really the measurement after the first physical prototype is the first time that you're doing anything really analytical. And what you tend to do is go through a number of cycles where you modify the design, make a new prototype, and retest. Well, that's very time consuming and it's very expensive, especially in the eyes of management, because the product is done except you're just squeezing a few dB out of the emissions. But if you look at the bottom, what we suggest is a flow that includes EMC analysis in the initial design of the board. So for example, if you can augment your signal integrity verification and sign-off with an emissions sign-off, then you have a chance to redesign for the emissions before you ever do a physical prototype. And you should be able to significantly reduce the number of physical prototypes done late in the design process. So this predictive design procedure yields fewer board spins, faster time to get the product done, and fewer post-production returns for maybe signaling conditions that you didn't test in your EMC compliance testing. Next slide. The types of emissions that we consider in our board and package tools is shown in the slide on the left. There are three types of emissions that are shown. The first two types we consider. The third type we don't consider in our analysis, and we leave that for an EMC engineer. The first type is from traces. Let's call it microstrip traces because a microstrip trace is exposed on one side to the open environment. So these could be signaling traces, as in a serial or parallel bus. They could be clock traces, and clock traces are especially susceptible to radiation for synchronous clocks. But anything that looks like a microstrip trace that is exposed either on the top or the bottom of the board can leak energy and is considered by our analysis. Also, power plane cavities or power ground pair cavities can radiate. They can radiate because they have power ground noise. They can be decoupled, but you still have edges that are not tied together all around the perimeter, and those edges can leak through an equivalent magnetic current. What we don't consider in Sigrity tools, but we would suggest more a 3D EM simulation approach, is emissions from a cable or possibly emissions from a heat sink. But as you'll see later, you can do a lot with your board for design side consideration and reduce tens of dB the emissions from your boards just from considering the microstrip traces and the power ground emissions. Next slide. This is the only equation in the whole presentation, and I'll be very brief. Basically what we do is it's just like running a SPICE simulation, where if you want to look at currents and voltages from a SPICE simulation, you put in probes. Well, when we run our signal and power integrity simulations, all you have to do is tell the software that you would like to calculate emissions when you're done. And we automatically define the probes, as you would in SPICE, to save all the results that can allow us to calculate the emissions. The results that we save are the branch currents in the figure on the left labeled J in purple, or we save the edge voltages at power planes in the figure on the left labeled M as the equivalent magnetic current at the edge of power planes. Once we've performed the simulation with the actual signaling conditions for signal or power integrity, we then do a post-processing step through what are called Green's functions, and that propagates those currents, either a J or an M type current, propagates those to both the far fields and the near fields. And that's how we're able to predict emissions. Next slide. So to show you some results, to give you some trust for what it is that Tanit's going to be talking about in optimization, the base level analysis capabilities that we have in our Sigrity software, up at the top, if you look, we're both measuring the near field and calculating the near field for a whole board. And as typically done, we're looking at the magnetic field in the near field, so probably about 1 centimeter above the board, we're looking at the magnitude or the spatial distribution of the magnetic field. On the left is the measurement, and on the right is a time domain simulation that's actually converted to frequency domain results. And what you can see is that the spatial distribution is about the same. So the hot spots are the same. Since these are plotted on exactly the same scale, you can see that the amplitudes are about the same. Now what this means is if you had an antenna that had a near field distribution that was this close to measurements versus simulation, you'd be very happy because you're going to get the correct amount of radiated power and you're going to get a good knowledge of where the energy goes in space. But if we zoom in even further on just the DDR block as indicated in the figure, you can see that both at a whole board level and even at a DDR block level where you have very well-defined switching activity occurring in the time domain, that both the distributions and amplitudes are about the same. So what this tells you is either at the macroscopic level of the whole board or as you push down to a block level or even an individual packaged device level, that the emissions are working fairly well. And so with that background and a bit of trust for Sigrity being able to predict emissions relatively well, Tanit's going to take off in the next few slides and talk about how to use this base level analysis capability to do automated optimization to reduce emissions. Tanit?
Thank you, Brad. Hi, my name is Tanit Virasapan. I'm an Optimize PI product manager. So today webcast I will mainly focus on EMI optimization. First, I would like to give a very quick overview on the device optimization, which we have in Optimize PI in the very first version. I have this example of a board that has a device on the power plane, and there's a lot of capacitor around the device, and there's a current coming from power supply, and as you can see the shape of this power plane. So on this device, if user not carefully choose capacitor, it can be power plane resonance on the device, and that can cause noise on the power plane. So we can take this board and do device optimization, which basically the tool will changing capacitor on the layout and trying to reduce the impedance looking from the device. And at the end, you will get the lower impedance because we have new capacitor combination that work best for this device and get the lowest impedance. However, as you can see from here, that there are some areas that have no capacitor at all. So this area can also cause the EMI radiation. Because when we're doing this device optimization, we're mainly focusing on the device, and on this area, it could be impedance peak that the device optimization will not reduce at the minimum. So this is the device optimization. And in the new version of the Optimize PI 11.0, we have EMI optimization feature that can reduce the EMI radiation. If we take the design, either we optimize from the device or not optimize the device, we take it in the EMI optimization. What the tool will do is, first the tool will look at the impedance everywhere on the power plane cavities. Not just one or two, we look at every spread the observation everywhere on the power plane cavity. So we monitor all these impedance, not only the device, we are also everywhere on that plane. And during the optimization, the tool will suggest, during the optimization, the tool will try different capacitors on this plane and suggest new EMI capacitor. The suggestion will be on location where to place capacitor and what value to be used on those locations. And with that, the user will see impedance after placing this capacitor. And what they will see is they will see that the impedance will get much lower than the original impedance because we have this optimized EMI capacitor placed on the device. And we have added a lot of automations in the EMI optimization. And we have, if user do the default setting, user don't even have to do anything in the EMI optimization setting. So that is a total automation. And user can do a device and EMI core optimization together by loading in the layout into the device optimization. After get the optimized device capacitor, then load it, and then do the EMI optimization. Then after that, they will get both device and EMI optimization. I'm about to show you the demo of the Optimi PI that do the EMI optimization. I will use this example that will explain how we can do the setup and how to look at the result. But first, we look at this example. As you see that I have one device, U1, and this shaded area, this power plane that carry current from VIM or the regulator to the device. And there are a lot of capacitor around the device. And as you can see from here that there are no capacitor at all on this large area of the power plane. So this can be causing the EMI radiation. And we use a Sigrity tool called Power SI. This is other Sigrity tool called Power SI, just to demonstrate how this plane can radiate the EMI. And we found that this power plane have the E-field radiation peak at around 600 megahertz. And we look closely on that, closely to 600 megahertz on this E-field, and we can see that the radiation, most of the radiation coming from this large area of the plane that do not have capacitor placed at all. So that's what we expected. How can we reduce the PDN emissions? Optimi PI first automatically set up EMI observations and EMI capacitor candidate location. This is automatically done by the tool. And from the picture below, you will see that on the left side, there's a white dot. These dots, they are EMI observation locations. Basically, the tool will observe impedance on this location. And the tool also set up for EMI capacitor candidates locations. These square boxes, these are the EMI capacitor candidates, which will be in optimization. And we have the capacitor library that during the optimization, the tool will testing this capacitor value from the library on these capacitor candidate locations. And we will do 100,000 combinations and determine the best EMI capacitor combinations. Now let me go to the demo that shows you the Optimi PI. This is the power plane and the ground plane you see in one picture. And this is the area of overlapping between power and ground plane. The device is on the right side, and we have VIM on the bottom side here. A lot of decap around the device. Because in this webcast we are focusing on EMI optimization, so I'm not going to go through the detail on the device setting. But quickly, I chose a couple of steps that we have here is the capacitor library. This is the capacitor library that can be used in the EMI optimization. The tool will testing this capacitor on the EMI candidate locations, which have been loaded already. And we have a mounted capacitor on the board. already set up for this device. And we have one device. And this step is for EMI optimization parameter. Actually, in this setup, everything has been set up already by the tool. So we have all these default settings. If user wish to change these options, that's totally fine. We have, I would like to take a closer look on this couple of tabs here. This setup is EMI grid setup. Basically, the EMI observation and EMI capacitor candidates, we use the grid size, and we have default grid, which will automatically generate the grid and generate the EMI observation and candidate locations. If user would like to have more grids, they can change it in here, and we will get a totally new set of EMI observation and candidates. And these are the list of capacitor candidates. So currently I have this 31 EMI capacitor candidates. This capacitor, each location will have this capacitor type candidate. The one with the checklist will be the one, the candidate for this for that location. Okay. And this capacitor can be, user can choose to place capacitor on the top layer or bottom layer, or they can have both as a candidate, top and bottom. So that's a choice. By default, we put it on the top layer. But if user already have capacitor mounted on the design, EMI capacitor already mounted on the design, but do not know what value to use, they can put the capacitor in this setting. But right now, I have no EMI capacitor placed at all. And user also can change the frequency range if they would like to have a different frequency range. But with the default, we will optimize the EMI from 10 megahertz to 1 gigahertz in this example. So this is very simple setting for EMI optimization. As I mentioned, user don't even have to change anything at all in here. Just load the design with the library and then run the EMI optimization. And I'm ready to run the EMI optimization, but I don't want to spend too much time on this simulation. I have the one that already done. After simulation and optimization is done, the user will see this result, which will show different scheme. First is original scheme. This is the original design that have no EMI capacitor, only have a lot of capacitor around the device. And it's showing the impedance everywhere on the power plane cavity. This is more than one location. I can go into each location one by one, and you will see that all of them happening to have a resonance at around 600 megahertz. So this is all the observation locations. And we know that we have now, we know we have this resonance at 600 megahertz. Then we have the tool will report the scheme numbers, scheme 1, 2, 3, 4, 5. Scheme 1 here is adding one EMI capacitor. If adding one EMI capacitor, all the observations will see this impedance. The resonant peak has been lower and pushed further to higher frequency. If we added two capacitors, now the peak is gone. So this scheme 2 maybe is a good scheme to use because it totally removes that peak. Next is user would like to know where to place this capacitor and what value to use on these two locations. So we will go to this draw capacitor placement. This is scheme 2, which is adding two EMI capacitors. It adds two EMI capacitors on this location and using 100 capacitor on both locations. So the tool will tell exactly where to place EMI capacitor and what value to be used on those locations. which usually people don't have idea or totally guess where to place the EMI capacitor. Sometimes they use a rule of thumb, placing one capacitor every square inch on the board, and end up having a lot of EMI capacitor. But the tool will exactly tell how many capacitors needed and what value to be used. If I use one capacitor, it will be this location with the 100 nanofarad capacitor. If I use two, it will be these two locations. If I use 3 capacitors, it will be these 3 capacitor locations, and with a different value. This one, the 100 nanofarad, and this one is 47 nanofarad. If I use 4, it will be this. All of them 100 nanofarad at these exact 4 locations. So here is the result that you can see impedance plot on all the observations everywhere on the board, and also you can see where to place the capacitor and what values to be used on this optimized feed. So that is the EMI optimization demo I have in the Optimi PI.
I know tonight you're going to go through a couple of cases, but we've had a couple of questions. One is someone was asking where the decoupling capacitor library came from.
Capacitor library can come from a user can generate it by themselves, or they can load it in the. We work with different capacitor vendors. We have so far 5 different vendors: KMET, Murata, TDK, Tiger Uden, and Samsung that already built it, integrated in the Optimi PI. User can use those vendor libraries, or user can create their own library. And also we have a Sigrity default capacitor library ready to use, and user can quickly use that library.
Okay. Also, we are taking questions via chat. For those of you who aren't seeing it, you go to the center top of your screen and pull it down. But there's one more question. I know you're going to go through another example or two. But I was asked by someone how long the simulation that you just showed would have taken. I know you didn't show it live, but how long was that?
This one, it takes about 7 to 10 minutes.
Okay.
On this tile board, this is a 4-layer board, and about 2 inch by 4 inches. Take about 7 to 10 minutes.
Okay. And the simulation time then depends on the size of the board and the size of the grid that you've used for observation points?
Exactly, yes. And with the result from the optimization, if I select the scheme number 2, which is adding 2 EMI capacitors on this location and 100 nanofarad on these 2 locations. And again, I use a power SI to demonstrate the radiated emissions before and after. As you can see, the red colored bar, this from the original design, which have the radiate a lot at around 600 megahertz. And after we adding these 2 capacitors on these locations, the radiation gets huge improvement is 44 dB at this frequency. And also we can look on this E field at 580 megahertz, and we can compare this on the same scale. You can see that it clearly show that it lower the radiation a lot.
Actually, if I can jump in for a couple questions that have come in. So one person is asking, what frequency did the peak get pushed out to? It
depending on the design and on the capacitor being added on the design.
Okay. And then another person is asking, does the tool take into account the connection inductance of the capacitors, which is influenced by the placement of the vias and the distance to the power ground plane?
Yes, very good question. Absolutely. Yes, we have to taking into account of the via, the trace, the plane, by connecting between the capacitor that we added to the design. That already taken into account, and we in the engine we calculated this loop inductance and resistance.
Okay, and another person is asking, I guess follow up on the question about where the frequency peak got pushed out to. There's an observation that question about issues at high frequency above a gigahertz emissions. So can you speak to that?
Yes, the peak will push out to higher frequency or and maybe a lower amplitude. And if you know exactly at what frequency is more important and what frequency you have a lot of current excitation, so those frequencies you have to watch out and try to move the peak away from those frequencies.
Okay, great. We'll let you go on. We've got a couple more questions. We'll circle back to that.
Okay. So, and we did a case study to see what the impact if we are not using the optimal location that reported by the Optimi PI. The top layer, the top picture here showing this is the location recommended by Optimi PI. These two locations using 100 nanofarad. But if you're using on other locations, not these two other locations, what would happen is when we look at this the E-field plot, we will see that the non-optimal location will have higher emission compared to the one from the optimal location. So that is a proof that the tool is totally gives the truly optimal location. And we also do it a little further by changing value of capacitor. The tool recommends 100 nanofarad capacitor, two of them on these two locations. But what if we use other values? What if we use 10 nanofarad capacitor? What happens is the non-optimal capacitor value will have higher radiation on this frequency. In this study, in this case, we are seeing between the 10 to 30 megahertz have higher emission if we are using a non-optimal capacitor value. And this emission that is E-field platform, other two power SI as I mentioned, but users don't really have to use the power SI to do this radiation plot. Everything can be done. Users just look on impedance plot from the Optimi PI and reduce the impedance everywhere on the power plane cavity. Optimi PI is effective for all board design types and size. I have other two examples to show the EMI optimization. This design have a narrow plane from VIM to devices. And you can see that there are from the VIM to the devices, there are no capacitor at all on this plane. And there are a lot of capacitors close to the two devices. If you look at impedance along the way on this plane before reaching the devices, we can see that on this plane, especially the area that far from the VIM and far from the device, there will be a resonant peak happening about 550 or 700 megahertz. And when it's getting closer to the device, the peak gets lower and lower because it has a lot of capacitors close to the device. And also when it gets closer to the VIM, the peak lower, it's getting lower because the VIM is close to the short circuit. So after the optimization, the tool recommends placing two capacitors on this location and using 10 nanofarad capacitor and 100 nanofarad capacitor. And with that, we will get much lower impedance everywhere on this plane. So this is a design that has a small, narrow plane. What if you have a large plane? It can also lead into the same issue as the small plane. On this large plane, there are example I have 5 devices and a lot of capacitor for these devices. But still, there are a lot of area of this power plane cavity that do not have any capacitor. And if we look at the impedance, everywhere on this power plane cavity, we will see that there are high impedance. There are a couple of high impedance peaks on this plane. And the tool, after the EMI optimization, the tool recommends a lot of these EMI capacitors, 100 nanofarad and 10 nanofarad, to be placed on these locations. And after placing these capacitors, impedance gets much lower. So as a summary, today many design engineers have no idea where and what capacitor, EMI capacitor to be used on their design. And many engineers spray capacitor on the layout, so that can end up a lot of capacitor. Optimized PI now can optimize EMI capacitor to reduce the power plane emissions. And we can optimize on the existing EMI capacitor that already mounted on the board, or the tool can recommend a new capacitor, giving a location and value. We are targeting for the ease of use, so we have a lot of automation that's been done. Users don't have to do a setup for EMI optimization, but we have an option for user to tweak the settings. And this feature is included in Optimized PI 11.0 at no additional cost. It's already available for beta version.
Okay, great. We've had a bunch of questions, so let's take a number of them. 2 people asked a very similar question about what kinds of design files can be accepted. One person is asking about Allegro, and one person asks more generally. And the answer is that we can certainly accept in layout databases from Allegro and really any of the popular PCB platforms. Actually, another question that I'll hand over to you, Brad. There's a question about how high within Sigrity the frequencies can go. It's asking about simulations that might go above a gigahertz, up to 10 gigahertz and so on. Could you speak to that, Brad?
Yeah, can you hear me?
Yes.
Okay. Yeah, basically you can say that there's no upper bound to it except for where the assumptions in the simulation would break down. And if you look at parallel planes and power delivery networks, that's very, very high in frequency. Where the simulations would tend to break down would first be where your signal integrity analysis would break down, and that would be in maybe 20 gigahertz range for VIA models and things like that. And so if you're going to 10 gigahertz, there should be absolutely no issues with the Sigrity simulations for emissions. If you're going to 10 gigahertz, you may end up getting more cable radiation and radiation from heat sinks and things like that you're going to want to consider with a 3D solver.
Okay, good. And then, Tanit, maybe to expand on a point, one person is asking, are the simulated results comparing the capacitor placements? And that really is the automation to look at all the different scenarios. So maybe you can comment a little more on that.
I'm sorry.
So the question was about are the simulated results comparing capacitor placement? And yes, they are. They're going through the various scenarios with one candidate location being used, many candidate locations being used. Can you talk about that optimization process?
Yes. In the optimization process, basically the first thing, the tool first set up EMI observations and everywhere on the cavity, on the power plane cavity, and also setting up a EMI capacitor candidate port everywhere on the plane. And on the port, and the tool also will extract the loop inductance and the loop in resistance of each capacitor, each EMI capacitor candidate. and then do the optimization. During the optimization, the tool will go to a capacitor library and testing a lot of capacitor types into each location. So we do 100,000 capacitor testing or iterations until we reach the best solution that can give the optimal solution.
Yeah, it's also interesting that when the second capacitor is used, it's not just in a second spot. It doesn't use the first spot plus another one. It found a better spot if there were two and different spots if there were three and different values and so on. Okay, and someone is asking if in the simulation the power plane to ground plane spacing is considered as part of the analysis.
Yes. We take the whole layout and we consider all the structure from the layout, power plane, shape, trace, via, stack up, dielectric and conductivity, everything from the layout.
Okay. Another
and for that one, it's considered in both the power plane itself, but also very importantly in the mounting parasitics for the capacitors.
Okay. And someone asked if we accepted Gerber or DXF files, and I think the answer to that's no. Yeah, I don't think we do. We're really accepting layout databases as a starting point for the simulation.
Yeah, the Gerber file have no electrical information.
Right.
That's why the Gerber can be.
Yeah, Leslie, let me address that real quickly. Yeah, Gerber is for manufacturing data. It has no component data or stack-up information in it unless you have an external tech file. As far as DXF data goes, that's common for packages, and we do have a flow that we call a speed edit flow that will take that, what we call dumb data, and intelligize it, but you still don't have component placements, which are your capacitors. So if you're looking at doing this post-layout type of a simulation with the capacitors and components indicated, you really want to start from an intelligent design database.
Okay, and since we're trying to keep to the time that we've scheduled, and we're already a bit more than half an hour, I'm just going to go through two more questions. We can take other things offline. There are a couple more questions that we'll get back to people on individually. So someone asked where we put our ports to observe impedance, and that really was the grid that was automatically set up in Optimized PI, right? Those grid intersection points serve as those observation locations. And then another person asked if the design already includes decaps, can they be considered right where they are as you're optimizing for additions?
Yes, absolutely.
Yeah. Okay, good. Let me see if there are any others that came in at the end. No, we'll leave it there. Thank you very much, all of you, for participating. There were a couple of questions about pricing and availability and so on, and we'll get back to you on those kinds of things offline. Thank you very much for joining us, and thank you, Brad and Tanit.